In this video, we continue focusing on carboxylic acid derivatives, molecules where we have a carbonyl group, like we have here, that's directly bonded to a heteroatom, where that heteroatom, such as oxygen, nitrogen, or a halogen, can act as a ready leaving group. In this particular video, we are going to transition from the last several videos where we focused on nucleophilic acyl substitution reactions where there was acid present, to instead focusing on situations where we instead have a basic nucleophile. So we can break these nucleophilic acyl substitution reactions into two categories: acidic conditions, which will be obvious based on seeing the presence of sulfuric acid or the term acid catalyst written or something else along those lines, wherein the first step of the mechanism is protonation due to the fact that there is a strong acid present, versus what we are going to focus on in the next few videos, which is where we have instead basic or anionic nucleophiles. So the way that you can recognize that the nucleophile is going to follow these so-called basic conditions, one of those ways is anytime you have an anionic nucleophile, it will fall into this category of basic conditions. You won't end up having an anionic nucleophile and an acid catalyst. Those two, being that one's basic and one is acidic, would react with one another. So therefore, it will be one or the other, not both. So in cases where you recognize that there is a basic nucleophile, we are going to follow the general mechanism that we will talk about in this particular video. Our starting structure for this nucleophilic acyl substitution reaction, again, is any of the carboxylic acid derivatives that we talked about in the earlier videos. So what that means is that the leaving group here could be an O-alkyl group. We could also abbreviate that O-alkyl group as OR, where R is defined as an alkyl group. That would mean that the functional group as a whole is an ester, because esters are defined as molecules that have a carbonyl group directly bonded to an O-alkyl group. We could also be referring here instead to an acid anhydride, which is where we would have an oxygen leaving group directly bonded to a carbonyl, directly bonded to some R group there. And that would be what we refer to as our acid anhydride functional group, or just an anhydride functional group for short works there as well. Additionally, other functional groups that we talked about as leaving groups here in our carboxylic acid derivatives and nucleophilic acyl substitution reactions additionally included amides, which would mean that we had a nitrogen atom directly bonded to two additional groups other than being directly bonded to the carbonyl. And those R groups could either be hydrogens or carbons there, and that would either way make them amide groups here, as a nitrogen leaving group would create an amide functional group there if the nitrogen is directly bonded to two hydrogens and or carbon atoms there. We also had the imide functional group, IMIDE, which had a nitrogen as the leaving group, and that nitrogen was directly bonded to another carbonyl. And here the nitrogen would have to have an R group there that is carbon or hydrogen to fill a complete octet, and then the carbonyl would also have another R group directly bonded to it over here, making this a so-called imide functional group. So with any of these groups, as well as an additional possibility of having a halogen there as the leaving group, where X is a halogen, and that would make this an acyl halide functional group. In any of these situations, the leaving group in each case will be, following our general template that we have looked at all along, the leaving group will be the heteroatom, such as the oxygen of the ester, oxygen of the acid anhydride, nitrogen of the imide or the amide, or the halogen atom here that's breaking away, as well as whatever groups those are bonded to further down the chain here. So the bond that is breaking in all of these scenarios during this nucleophilic acyl substitution will always be this bond to the leaving group. And here, as we focus in this particular video on basic or anionic conditions, what we're generally going to have is a situation where we have a nucleophile, Nu, that is bonded to a metal, M. And what happens there is that the metal, since there's a large electronegativity difference between the nucleophile and the metal becomes a cation, and the nucleophile takes the electrons from that bond to give it a lone pair there, and a negative formal charge, enabling that nucleophile to act as an anionic or basic nucleophile. So let's take a look at the general mechanism for this reaction, and then we'll spend the next few videos going through some specific scenarios where these types of conditions are in place and the types of specific reactions that this mechanism can be used for. Much like with the mechanism for the reactions under acidic conditions, I'm not going to give you every single possible scenario and every single possible example where you could work with a carboxylic acid derivative and do this type of reaction. Instead, what we will focus on is the basic fundamentals so that you can then apply that to any situation you run into where you have any carboxylic acid derivative reacting with a basic or anionic nucleophile to give the final product that corresponds to substitution of the leaving group, LV, in our starting material with the nucleophile in the product. So let's go through the general mechanism for this type of reaction. And so what you will be looking for here in this general mechanism is this mechanism is going to be in play anytime you have an anionic basic nucleophile. So these will be situations where when you look at the reactants, you do not see H plus written, you do not see H3O plus, you do not see H2SO4, you don't see the term acid catalyst, and so on. So in this reaction mechanism, what we will do here is we will start with our carboxylic acid derivative. That's going to be our carbonyl group from the carboxylic acid derivative. R is whatever group it's bonded to here on the left. That's going to be carbons or hydrogens. And then on the right here, we have our leaving group. The leaving group has to be a heteroatom, meaning a non-carbon, non-hydrogen atom that is directly bonded here. Otherwise, we won't have a good leaving group, because if we try to break a carbon away or break a hydrogen away, the product of the reaction would be very, very unstable. We can't break carbon-carbon bonds readily. It would yield an unstable carbanion ion, or in the case of hydrogen, a hydride product by breaking that bond and taking the electrons with it. So we need a heteroatom there in order to create a good leaving group. We'll react here in this mechanism with our nucleophile, which is going to be a metal directly bonded to the nucleophile. You may see this written out like I have here, where you have the cation and anion listed, or you may just see it written in a more abbreviated common format as MNU. And you will have to decipher that whenever you have a metal directly bonded to something from the right side of the periodic table, that bond is ionic, and so the nucleophile is going to act as an anionic nucleophile. So in this mechanism, what's going to happen is that when you have the anionic nucleophile paired with our molecule that has a leaving group and carbonyl, this carbonyl group has a carbon that's very positively polarized. For one, by resonance, we could show a second resonance structure where we had taken the pi bond up onto the oxygen to put a positive formal charge on this carbon. That illustrates to us that since one of the resonance structures would have a positive charge on this carbon is very strongly polarized. Additionally, by induction, the oxygen is electronegative, so we're pulling electron density toward itself by that feature as well. As a result, we have a very electrophilic carbonyl carbon. As we have seen before, whenever we have a carbonyl carbon, it is naturally electrophilic. So what's going to happen is that nucleophiles, particularly relatively strong anionic nucleophiles, are going to be eager to attack that positively polarized carbonyl carbon. And so what will happen here is that the nucleophile, using its lone pair of electrons, is going to come in. It's going to form a covalent bond here to the carbonyl group. And we can't do that alone because that was all we did. We would go over the octet rule. So we have to take the pi electrons and move them up onto the oxygen. So let's go ahead and write out the intermediate that would result from that. That carbon now is going from a carbonyl, which was sp2 and trigonal planar, to a carbon with 4 bonds to it, which means it's going to be a tetrahedral carbon, and sp3 hybridized at the moment. I'm going to go ahead and write out the structure here. So what we originally had is our carbonyl carbon. I'll highlight here in red in the starting material, red highlighted in the product. Our leaving group is still attached to that carbon, so I put LV in there. And now we have a new bond to the nucleophile And I'm going to put that new bond here in green for emphasis on the product side and the nucleophile attached there. Now, at this point, I'm going to go ahead and label what this step was, which was the step 1 of the mechanism is that the anionic or basic nucleophile is going to directly attack the carbonyl carbon. So we've done that. Now, at this point, we mentioned that the heteroatom leaving group that we have is going to be a pretty capable leaving group, that the bond between carbon and the leaving group is relatively weak, and when we break this away under basic conditions, it will yield a relatively stable anionic product. And so what we can show here is, as the next step, and actually the final step of this mechanism, is that we will reform the carbonyl. And in order for that to happen, the leaving group, heteroatom there, has to break away. That restores the carbonyl group that was present in the original molecule. The R group, that is the carbon or hydrogen-containing group over here, is still present. The leaving group is left, and now we've replaced it with a bond to the nucleophile. So I go ahead and put in my NU for nucleophile. And I can also show that the leaving group has broken away, so I'll put plus LV. And since when the leaving group broke away, it took this pair of electrons that I'm highlighting in the reactant, it took that pair of electrons with it, because the arrowhead ends up on the leaving group. That indicates to us that we need to put another lone pair of electrons in that leaving group, and that leaving group is generally going to take on a negative formal charge. So in step 2, we can describe this as the carbonyl reforms, and the leaving group leaves. Now, you will notice in this particular reaction mechanism, as is going to be true for all of these anionic basic nucleophile reaction mechanisms, at no point do we create any intermediates that have a positive formal charge. The formation of intermediates that have a positive formal charge is unfavorable when we are working under anionic or basic conditions. And that is what we have here because we have our basic or anionic nucleophile. And so that's a key thing to keep in mind whenever you're writing out these sorts of reaction mechanisms that are conducted under basic conditions, is when you conduct reactions under basic conditions, it is unfavorable to create intermediates that have positive formal charges. That is not only true here for nucleophilic acyl substitution, but generally true is that if you're working under basic conditions, where we're recognized based on the fact there's an anionic nucleophile and no acid present, we avoid making positive formal charges on any of the intermediates. So as you look through here, we favor anions throughout. We have an anionic nucleophile, anionic intermediate, anionic leaving group, and that's going to be true all the way through. In contrast to that, when we're working with this mechanism and others that were done under acidic conditions, where we had an excess of positively charged protons, instead, in those situations, positive formal charged intermediates were favorable and negatively charged intermediates were unfavorable. So the situation and the preference here is opposite depending upon whether you're working under basic conditions with anions or under acidic conditions with protons. Proton favoring conditions, acidic conditions in other words, are going to result in intermediates that have positive formal charges, whereas anionic conditions are going to result in intermediates that have negative formal charges. And under anionic conditions, we avoid forming intermediates with positive charges. Under acidic conditions, we favor positive charges and disfavor negative charges on any of our intermediates. So keep that in mind as you're kind of differentiating between different types of reaction mechanisms. That's a good overall rule to have in place. So as we continue onward from this general mechanism, what we're going to do in the next few videos is look at various permutations of this general mechanism where we're working with specific nucleophiles that are common, specific heteroatom leaving groups, and things like that to apply this general mechanism that we're looking at here. As I've said before, don't expect to see an example of every single type of carboxylic acid derivative reactant and every single type of anionic nucleophile that you might run into. You should instead be able to take this general information and apply it to a variety of different scenarios where you have whatever anionic nucleophile I would throw at you and whatever carboxylic acid derivative I might throw at you.